All right, welcome to the Explainer. Today, we are diving into a theory, and honestly, it's so ambitious, it tries to rewrite the very rules of reality as we know it.
So get this brand new theory, which was actually born from a dialogue between a human researcher and an AI, is claiming that the entire universe runs on just one single simple law. We're talking everything, from the tiniest atom to the biggest galaxy, even to our own thoughts. They're all supposedly following the exact same fundamental pattern. It's called fractal relational mechanics, and wow, it might just be one of the most out there ideas we've ever talked about here.
So, you gotta ask, right? Where does an idea this radical even come from? Well, usually, ideas like this are born from a really big problem in how we already see the world. And believe me, modern physics has a big one. Yeah, the source material does not pull any punches here. It calls the current state of physics a conceptual schizophrenia. I mean, that's a seriously powerful way to put it, and it really gets right to the heart of the issue. Okay, so think of it like this. On one side, you've got general relativity. That's Einstein's baby, right? It describes the big stuff, stars, galaxies, as this smooth, continuous fabric. The source calls it a magnificent cathedral. Then, on the other side, you have quantum mechanics. It describes the teeny tiny world of atoms, and it's all jumpy, granular, and based on probability. Another magnificent cathedral. So, what's the problem? Well, these two cathedrals are built on foundations that are fundamentally at war with each other. They don't work together at all. And look, this isn't just some abstract problem for physicists. This conflict actually forces us to invent, well, ghosts to make our math work. It's kind of wild. We look out there, we see galaxies spinning way too fast to hold themselves together, so poof, we invent dark matter to glue them down. Then we see the whole universe expanding faster and faster, so poof again, we invent dark energy to push everything apart. This new theory, it's basically saying, hey, these aren't real discoveries, they're just fancy names for the stuff we don't understand. So how in the world do you solve a problem that big? The theory says you don't just put a Band-Aid on the old ideas. Nope, you have to dig all the way down and build a brand new foundation. And that's exactly what it proposes. A whole new way of looking at reality, one that shifts our focus away from things and onto relationships. Now, this is where you need to buckle up because this idea completely flips common sense on its head. The core concept is this. The universe is not a big empty box with stuff floating around in it. No, the universe is the network of relationships itself. It's a self-creating fractal web. So everything you see, a star, a planet, even you're not a thing. You're a stable pattern within this giant cosmic web. So what's driving this whole network? Well, according to the theory, it's just one single, simple rule. They call it the meta-law, or the tuning equation. And you can kind of think of it like a universal desire for harmony. Every single piece of reality, from a quark to a galaxy cluster, is constantly adjusting itself, trying to get into better sync or coherence with everything around it. That's it. That's the engine that drives the whole show. And from this one big idea, this drive for harmony, three really key principles pop out. First, there's relationality. That means nothing exists on its own. An object is defined by its connections. Second, you get fractal scalability. This just means that same simple rule of harmony applies at every single level, from the super small to the super big. And third, and this is a big one, the holographic principle. The idea that the 3D world we see and touch is really just a projection, kind of like a shadow being cast by that deeper relational network. Okay, let's pause. I know, that is a lot of mind-bending philosophical stuff. But is any of it actually science? Because for it to be science, it has to make predictions that we can actually test. So, how did they do it? How do you even start to test an idea this huge? Well, they used a really cool method they call holographic reverse engineering. And the analogy they use is just perfect. Imagine you're in Plato's cave. All you can see are shadows on the wall. Your job is to study those shadows so closely that you can figure out what the real objects casting them must look like. That's what they're doing.
They're looking at our measurable 3D shadow world to try and figure out the rules of the deeper reality. So, to build their model of how atomic nuclei work, how much data do you think they needed to feed into it to get it started? 100 data points? 1,000? No. They used just one. They tuned their entire model so that it would correctly reproduce a single known fact: the mass of a proton. That's it. Everything else that came out of the model after that was a pure hands-off prediction. And folks, this is where the story gets absolutely wild. With the model calibrated on just that one number, they just let it run to see what it would predict. And from that one single rule, an incredible cascade of results started pouring out. First up, their very first blind test. Could it predict the mass of the neutron? The answer was yeah. And not just kind of close, it was astonishingly accurate. We're talking an error of about 0.001%. Remember, they didn't tell it this number. This wasn't programmed in. It just emerged from the model's basic rules. But okay, one good prediction could be a fluke, right? So they kept going, using the exact same rules, and this is key. They didn't change a thing, no new tweaking. They started simulating more complex atoms. And just look at these results. They predicted the binding energies for deuteron, helium, carbon, and the numbers are practically a perfect match for what we see in real-world experiments. It really seems like this model has somehow captured the fundamental rules of what holds an atom's core together. And then, something happened that they weren't even looking for. It was completely unexpected. While they were running the simulation for carbon-12, the model flickered into this temporary higher energy state before it settled down. They checked the numbers and they couldn't believe it. The model had spontaneously, all on its own, discovered the Hoyle state. This is a very specific, very special energy level that is absolutely essential for stars to be able to create carbon, which, is the element that all known life is based on. The model just found it. It wasn't programmed to. Okay, let's be honest. Those results are pretty stunning. But we all know the saying, extraordinary claims require extraordinary evidence. So we have to take a step back and put on our skeptic hats. Is this a genuine revolution in physics? Or is it just a really, really clever mathematical trick? And what's really important here is that this critical look comes from the authors themselves. They're the first to point out the strengths, right? The beautiful simplicity of it, the incredible predictive power. But they also point out the biggest weakness. The argument from critics that this might just be a very fancy form of parameter fitting, basically twisting the knobs until you get the right answer, not a real discovery. That's why they themselves call it proto-science. It's not proven science yet, but it's an idea that's ready and waiting to be tested. So how do you make that jump from a cool idea to actual science? Well, you propose an experiment that can either prove you right or prove you wrong. No wiggle room. And that's exactly what they've done. The idea is to take something called a Bose-Einstein condensate. It's basically a cloud of super cold atoms that all act like one big mega atom, and then use magnetic fields to mess with its internal harmony. And here's the wild prediction. If you change only its harmony, its internal coherence, you should actually be able to change its total mass. If that experiment works, it changes everything. If it fails, a huge piece of the theory comes crashing down. And so that leaves us with the biggest, most profound question of all, doesn't it? What if mass, the thing we think of as the most basic property of stuff, isn't fundamental at all? What if it's just an emergent property, a side effect of harmony, just a number that tells us how coherent and well-ordered a system is? It is an absolutely staggering thought, and for right now, it's a question that is very much open.